All right, so I wanted to make sure that you had an example with a basic buffer and calculating the pH of a basic buffer. And we're going to do this in one of two ways. We're going to use the new Henderson-Hasselbalch equation, but then I'll also show you a more traditional route forward for calculating the pH. It really doesn't matter which route you choose as long as you're comfortable with using it. All right, so the Henderson-Hasselbalch equation that we had learned previously was for an acidic buffer. pH equals pKa plus the log of a salt divided by an acid. We need to rewrite this now for a base solution. Okay, so essentially instead of pH, we're going to rewrite this for pOH, since that's on more of the basic scale. Instead of pKa, we're going to put in the pKb plus the log, and of course the salt is going to stay the same. And then on the bottom, instead of having my acid, we're going to put in the base. Now let's take a look at the problem above here. It says calculate the pH of a 0.15 molar NH3 solution in 0.11 molar NH4Cl. Remember, the majority of your basic buffers are going to be the difference from your weak base. You're going to add in an extra hydrogen and then have an extra anion. Well, this is pretty characteristic here. So I have an extra hydrogen in my NH3 becoming NH4, and then I have the addition of an anion. And this anion could have several different charges, so you might need several of your bases in here, but luckily we have one that has a 1-to-1 ratio. So let's start plugging and chugging here. The other piece of information that you may need to know for this problem is that the Kb of this lovely base is 1.8 times 10 to the negative fifth. So we'll have to use that as we're going forward with this problem. Now, pOH is of course what we're trying to solve for. pKb is the negative log of the Kb. That's 1.8 times 10 to the negative fifth, plus the log, our salt concentration. That's really after the NH4 1+ concentration. We really don't care about this anion now, because the common part of this is going to be that NH3. That NH3 became the NH4. That's the yin and the yang component. Now, luckily, there's a 1-to-1 ratio here, so I can just straight up use that lovely concentration. So my salt concentration is 0.11 divided by my base concentration. That's NH3, and that would be 0.15. Now, straight to the calculator we go. And I'm going to grab that. So let's take the negative log of 1.8 times 10 to the negative fifth. And plus the log of 0.11 divided by 0.15. All right, I'm getting a pOH of 4.6. Now remember that the question did ask for the pH, so you still need to subtract this from 14 and report that number. So let's see, 14 minus that answer would give me a pH of about 9.4. 9.4. Now, I really like the Henderson-Hasselbalch equation because, again, it is so plug and chug. But if it's not something that you're comfortable with, you still can use traditional ice problems to solve this thing as well. You're going to start off with the hydrolysis equation for the NH3. So the NH3 reacting with water. Bases like to snarf up a proton, so feed it a proton and let it become NH4 1+. And then, of course, you're going to have hydroxide left over. That hydroxide is the key to unlocking the pH. We'll get ready for our ice problem. Now let's plug and chug in the concentrations that we know. We know that the base has a concentration of 0.15, and the salt with that common ion of the NH4, that concentration is 0.11. Now water doesn't matter, and the hydroxide would initially be 0. The KB for this base is 1.8 times 10 to the negative fifth. So we can ignore the change to the initial concentrations and define the hydroxide ion concentration as X. So at equilibrium, I have 0.15, 0.11, and X. Now, luckily, mathematically, this is going to be a pretty easy problem to solve. So this is going to equal X times 0.11 divided by 0.15. And let's find our X value. I actually calculate that it should be equal to be about 2.5 times 10 to the negative fifth. That represents the concentration of the hydroxide. So if you negative log that, you get the POH. And this is where students traditionally have a hard time. They jump right to pH with this. The POH here would equal, oddly enough, 4.6. Subtract it from 14 to get the pH, and we equal 9.4. Interestingly enough, the exact same pH that we did before. So what the Henderson-Hasselbalch equation really allows you to do is just to save some space and kind of cut through the red tape with having to go through this whole ICE problem and get right to that pH. If this is something that you prefer, I would use this. Otherwise, I'd set yourself up for one of your traditional ICE style problems.